Today, we're diving into a fundamental truth of science, something that's baked into every single measurement ever taken. We're talking about doubt, but not in a bad way. See, in science, a little bit of doubt isn't a mistake. It's a core principle of how we understand the world. So, let me just ask you this straight up. Can you ever measure something perfectly? I mean, think about anything. The length of your desk, the weight of an apple, the time it takes to run a mile. Is it possible to get a perfect 100%, absolutely no error measurement?
Well, the answer from science, and this might actually surprise you, is a clear, resounding no. In the world of measurement, perfect just isn't a thing.
Okay, there is one small exception. You can count 5 books on a shelf, and you know there are exactly 5. Counting things one by one, that's an exact science. But the moment you switch from counting distinct items to measuring a continuous quantity, well, that's when everything changes. And this unavoidable doubt, it actually has a name. It's called measurement uncertainty. And I want you to get this straight. It is not a mistake. It's not a failure. It's just a basic property of our universe that every single measurement will have this tiny little window of doubt attached to it.
But why, right? I mean, we have lasers and atomic clocks and super advanced tools, so why can't we nail down a perfect number? Let's break down where all this doubt is coming from.
It really boils down to 3 main things. First, the instrument itself. Every single tool, whether it's a simple tape measure or a high-tech gizmo, has physical limits. Then you've got the observer. That's you. Our eyes, our reaction time, they're just not perfect. And finally, there's the environment. Tiny changes in temperature or humidity or even air pressure can gently nudge the results. So if we know this doubt is always going to be there, what do we do about it? Well, scientists don't try to hide it or sweep it under the rug. Nope. They do something brilliant. They put a number on it. They build the uncertainty right into their results, being totally honest about the limits of what they know. Let's make this real. Grab a ruler in your mind. You line it up, you find the smallest marks on there, probably millimeters. But when you look super close at where your object ends, it's almost never perfectly on one of those lines, is it? It's always a little bit in between. And that tiny gap right there, that's where uncertainty is born. It forces you to make your best guess.
You know that smallest little marking on the ruler? It has an official name. It's called the least count. So for a regular ruler, that might be 1 millimeter. That's the most detail that tool can possibly give you.
And here's the really cool part. Science has this elegant, super simple rule of thumb for calculating the uncertainty from your instrument. You just take that least count, that smallest division, and you cut it in half. That's it. So, for example, if your ruler's smallest marks are 0.1 centimeters apart, you divide that by 2. And boom, your uncertainty is plus or minus 0.05 centimeters. This gives you a clear, honest range where the true value almost certainly lives. This means you don't just say the answer is 10.3 centimeters. A scientist would write it as 10.3 plus or minus 0.05 centimeters. It's basically their way of saying, hey, my best guess is 10.3, but I'm being real with you. The actual value could be anywhere from 10.25 up to 10.35. It is literally honesty, written in the language of math. And don't for a second think this is just an old school ruler problem. You know when you step on a digital scale and the last number flickers back and forth for a second? That's uncertainty. It's the same exact principle. It doesn't matter if the tool is analog or digital. Uncertainty is always there. It just might look a little different. So we can't get rid of uncertainty completely, but that doesn't mean we're helpless. In fact, scientists have some really powerful ways to wrestle that uncertainty down and make their measurements way more accurate. And what's the most powerful technique of all? It's something you've probably done before. You just take a bunch of measurements and then find the average. It's that simple. By doing this, you let all those tiny random errors start to fight each other and cancel themselves out. Look at this. It's a perfect example. Say you're timing a pendulum swing. The first time, you clock it at 1.52 seconds. The next time, maybe your thumb was a little slow, you get 1.55. Then you're a bit quick on the trigger and get 1.49. You see that little dance they're doing? But look what happens when you average them all out. You land on a much more stable, much more reliable number, 1.52 seconds. All those little random wobbles, being a fraction of a second too late here, a fraction too early there, they tend to wash out in the average. It's an incredibly simple act that pulls your final answer much closer to the actual true value you're trying to find. And all of this brings us to what I think is the most important idea here. We need to completely reframe how we think about uncertainty. It's not a flaw. It's not some mistake we should be ashamed of. In science, uncertainty is a feature, not a bug.
And this quote just says it all, doesn't it? When a scientist reports their uncertainty, they are not admitting they messed up. They are proudly and honestly stating the limits of their tools and their methods. It's a sign of total transparency and scientific rigor. It's a badge of honor.
So let's just lock in the big ideas here. Number 1, perfect measurement is a myth. A little uncertainty is always there. Number 2, we can actually put a number on that doubt using that plus or minus value. And finally, and maybe most importantly, we have a powerful tool to reduce it. Just take multiple measurements and find the average. Which kind of leaves us with this one last big, fascinating question. If every single piece of data, every measurement, has its own little cloud of doubt around it, how on earth do we build scientific theories that we feel so certain about? How does all that individual doubt add up to collective confidence? Well, that's the magic of the scientific method.